Okay, so welcome back to another video. So here we have an infinite product series. So our index starts from n is equal to 1 to infinity. Inside the bigger quantity we have is 1 subtract 1 divided by 2n plus 1 quantity square. And then the exponent we have is alternating -1 to the power n multiplied by 2n plus 1. So we got a bunch of things going on. We have something in terms of like odd terms / indices we're dealing with. We have an alternating, term that we're working with as well. Yeah, a pretty gigantic product series. So you might be wondering how we can actually tackle such infinite product series as something as this ginormous. So a lot of stuff comes from, there's a bunch of formulas we'll be using in terms of its series representation. Well, actually the first step we're actually going to use, so just to get this out of the way, is we're actually going to call some infinite product series in forms of a function. And then afterwards, the thing is that the whole goal is to actually evaluate it such that we just plug that number into the end to actually get the given in the easiest way to get into the form of our, final answer that we want to achieve for by doing so. So a bunch of calculus going on. There's actually a special number that's being utilized as well. Some integrals actually that we'll be actually getting a little bit are getting creative on that side of the things. So just expect for a lot of things going on. So it's actually a pretty fun ride for what's about to happen with this whole, workload process. So with that, why don't we actually just jump right in. So as I mentioned, first step, we're going to call a function. Let's just call this p of x, for example. So we're actually going to let that be equal to this infinite product series. So infinity, n is equal to 1 of 1 subtract. So instead of 1, we're actually going to let the function, we're going to let this be x squared and then divided by, so 2n plus 1 quantity square. And then the same thing applies to the rest, -1 to the power n, and then multiplied by 2n plus 1. So as you notice, if I just plug x is equal to 1, p of 1 is exactly the given that we are trying to evaluate. So assuming assuming the continuity exists, so why don't we actually take the natural log of both sides? So the natural log of p of x. And so what I'm going to do here is going a few steps further, I'm actually going to add and subtract a 0 term, and then doing things ahead of time. When you take a natural log of the product series, that means you're actually taking the sum of the natural logs of those arguments. So doing all this back, so what we're going to have is, so let me write this first and I'll explain the details in a sec. So now we have, so this is going to yield us negative natural log of 1 minus x squared, and then add this with our infinite sum. So our term is going to equal 0. So actually notice that, so let me first write this out, -1 to the power n, 2n plus 1, and then multiply by the natural log of 1 subtract x squared divided by 2n plus 1 quantity square. Okay, so as you notice that I have a negative ln of 1 minus x squared. So where did that come from? Because I did say that we're actually going to add a 0 term. So if you actually evaluate at n is equal to 0 for over here, for this entire thing, you're actually going to get the exact same thing listed over here. So it's actually minus and then plus, and then the rest so far after taking that natural side is actually just this expansion from the top over here that we actually take the natural log of. So it still applies, so we're actually getting a little creative with this sort of thing. So next thing I'm going to do, let's actually take the derivative of both sides in respect to x. Differentiate both sides. So I have d over dx of the natural log of p of x. Okay, so now let's actually perform our differentiation. So this is straightforward to do. We know that this is going to be 2x divided by 1 minus x squared. Okay, and the next thing is differentiating this. This is the only x term inside, so we just have to, be careful how we actually tackle such things because we are inside in the world of, the world of n within our summation. So performing all this stuff out, we're going to get 2x, and then now we're going to have our infinite sum. So n is equal to 0 of -1 to the power n, and then multiply by 2n plus 1. All this being divided by 2n plus 1 quantity square, subtract x squared. So there's a lot of things going on, especially we notice that this is such a crazy, it's sum that we're going to be working with, but actually we're just going to treat that as a given and as an optional exercise for you guys to solve. You can comment below. You can actually try to solve this yourself to show that this infinite sum over here, specifically in the brackets, is going to come down to pi divided by 4 multiplied by secant of pi times x divided by 2. So with that, that's our given. Again, I leave it up to you guys. The proof is left as an exercise, as they would say. If you actually would like to calculate this infinite sum by yourself to show that this is equal to this following over here. Okay, so with that being the case, moving forward, so now why don't we actually do some integration? So let's integrate both sides from 0 to 1. So 0 to 1, and then we still have d over dx of the natural log of p of x, then of course dx, and then differentiate, so integral from 0 to 1. So now inside everything is going to be, so 2x divided by 1 minus x squared, and then now minus, so I've just multiplied all this back over here, so 2x times this entire thing. So now I have pi times x, and then divided by 2 multiplied by secant of pi times x divided by 2, and then just close it off with dx. All right, so as you notice over here, so integrating a derivative, so that's just going to get rid of itself, and then we evaluate this from 0 to 1, so that leaves us with just ln of p of 1, and then, well, didn't mean to close that off. Well, actually, yeah, no, that's correct. Close that off, and then subtract the natural log of p evaluated at 0. So the good news is that if I actually were to plug 0 back into our original function that we just called for, this entire thing is actually just going to yield to just 1. So just to leave a little note, p of 0 is equal to 1. So that means if I just plug that back into the value, ln of 1 is, of course, just 0. So we're just left with ln of p of 1 by itself. Okay, and so now to calculate this side. So what we're going to do here is let's actually do a little bit of a u substitution over here. So what we're going to use is we're going to let u, so let me actually put an arrow over here. We're going to let u equals pi times x divided by 2. So then that has to mean that du is going to equal to just pi divided by 2 and then dx. Okay, so I'm just going to keep this in the red, in the black, so put this away. Okay, so now we have our u substitution, so now let's just plug everything back into here. So as we see that if I have to change the bounds of integration, so if I plug in 1, that's going to be pi over 2 on the top. If I plug in 0, it's going to be 0 on the bottom, and then the differential on the bottom, so dx, so just divide that by both sides, so it's going to be 2 divided by pi, it's a constant. So I have 2 divided by pi, so our bounds from 0 to pi over 2. Now if I just plug this everything back, so 2 then times, what is it? 2u times 2u divided by pi, so I were to solve for, x by itself, just by doing so, then subtract 1 minus, so do the same thing, 2u pi and then square, and then subtract, so this is going to be u, and then times secant of u, and then close it off with du. Okay, so now that's what we're ending up with. So now to continue forward with this calculation, so far to reiterate everything, so we have shown that we're just left with just ln of p of 1. So ln of p of 1, and then now just evaluate all this together. So we're going to have 2 divided by pi multiplied by 0, the integral from 0 to pi over 2 of, now just to expand all this out from over here specifically, we're going to have 4 pi times u, and then divided by pi square minus 4u square. And then to rewrite things, I'm going to write, instead of secant u, I'm going to write this 1 divided by cosine u, so u divided by cosine of u, and then du. Okay, so now here comes the next thing. Let's actually do yet again another u sub. So I'm actually just going to call this variable. We're going to now let this be the letter v. So let's go to red with this one. We have a variable v, but let me actually write this as u. So u is going to equal pi divided by 2 subtract v. So as you notice, we have a cosine of u. So actually, we're going to be doing a little bit of some trig identity. We have to, do a bit of a substitution. So now putting all this back together, so that means, what is it? Du is going to equal to just negative dv, of course. So now we have 2 divided by pi. Change our bounds, so actually this is going to switch, and as you look at it, so this is going to be 0 on the top, this is going to be pi divided by 2 on the bottom. Then putting this back together, so I have 4 pi, then pi divided by 2 minus v. Next thing is pi square subtract 4 times pi divided by 2, and then minus v quantity square. Then on the top, so pi divided by 2 minus v, and then on the bottom is going to be cosine of pi divided by 2 minus v on the bottom, and then just substitute that with negative dv, the substitution. All right, so the next step, we're actually gonna, switch our bounds, so that'll become negative. That's negative over here, so that'll get rid of by itself. Then the next thing over here is we have all this, cleaning up that we have to do. There's a long things going on over here. So to put things a little bit easier, And then another thing, what I'll do is that we're also going to factor out the pi. We're also going to factor out the pi divided by 2, and then also apply some linearity. So we're actually going to have some, sum/differences of integrals that we're dealing with. So to put this all together, and if you want to check this to validate yourself, you're going to have the following. So if I factor out the pi divided by 2 from here and then here, but actually the v is going to stay by itself from here. So this is going to get rid of the 2 divided by pi on this side, and I have pi divided by 2. This is going to be 0. All that's left on the top is pi minus 2 times v, and then divided by pi times v minus v squared, then minus 1 divided by, so cosine of pi divided by 2 minus v, we'll be using that identity. That's going to be the same thing written as sine of v, then dv. And then the last thing is, again, the whole linearity thing going, that spiel going on. So we still have a v and then divided by this whole thing over here. So that means we're going to be left with minus, and then it's still associated with the 2 divided by pi. So don't forget about that. So minus 2 divided by pi from the integral from 0 to pi divided by 2 of, v divided by sine of v dv. Okay, so yeah, there's a whole lot of things going on, a whole lot of cleaning. I basically had to, do the long work, but to make sure that everything validates over here, but skipping all the little details and getting to is where we're supposed to be at this very moment. Okay, so now moving forward is now we have some special numbers we're going to be using. Well, not some, but a special number. So we're going to note the following. Have you ever heard of Callan's number? So we actually have that the following integral representation is represented as follow. 1 divided by 2 from the integral multiplied with the integral from 0 to pi over 2 of x divided by sine of x dx is going to equal to the letter g, aka Catalan's constant. So write it like this. So that means I can actually just replace this by saying that this is going to equal to just 4 times pi. Actually 4 times g, g being Catalan's constant. I have to restate that again just to make sure. 4 times g and then divided by pi. So that's that integral taken care of. We just now have to figure out how to solve this integral right here. Okay, so I'm actually just going to switch to different mark for this step. So now, as mentioned, this is the last thing that we have to calculate. This is kind of the difficult challenge on how to integrate such, this monstrous integral over here. So after doing a lot of playing around, there's something we got to check out that's actually going to blow your mind. That I think that's pretty crazy. So let's notice the following. If I take the derivative of this following function, so specifically the natural log of x times pi minus pi squared, and then divided by tangent of x divided by 2. So yeah, there's a lot of things going on over here. So I'm just going to put it equals over here. Equals, so expanding this out, we have a lot of things going on. You have a natural log, so we have a 1 divided by whatever's the input here, but you just flip that reciprocal just to cancel out, the whole, fraction under that denominator. So expanding all this out, and then you also have to take the derivative of this, which you have to apply the quotients rule. So doing so, you're going to get this following expansion. We have 2 pi, then times tangent of x divided by 2. Oh, I hope I have room for this. 4x tangent of x divided by 2 minus pi times x secant square of x divided by 2, and then plus x square secant square of x divided by 2. Just barely. Okay. And then on the bottom is that we're going to have 2 times tangent of x divided by 2, and then multiply by, so pi times x and then minus x squared. Yeah, so that doesn't look exactly what we're given over here. I know we're dealing with x, for example, but again, dummy variables, we can change that, it's totally fine. So yeah, this does not look like the same as this, right? But there's some cancellation that we can actually do here. So what I'm gonna do here is that I'm actually going to factor out and actually split this up in terms of like the sums of fractions. So doing so, we're gonna see that for one, I'm actually gonna separate it so that where my finger is, so these 2 terms and then the last 2 terms are actually gonna be on a separate fractions of its own. So by applying this, I'm actually gonna first factor out the 2 times tangent of x divided by 2. So from there, that means from these 2 terms over here, I'm left with just pi minus 2x. And then on the bottom, so I have a 2 times tangent x, tangent of x divided by 2, and then pi x minus x squared. Okay, you see something cancels out. All right, cool. Let's take things one step at a time. And then the next thing is that I have a secant squared x divided by 2, so let's factor that out. Secant squared of x divided by 2. And so what we have is pi x minus x squared. And on the bottom is going to be 2 times tangent of x divided by 2 of pi times x minus x squared. Some terms cancel out. All right, cool. So let me first cancels, and then what is this? Cancels, and then cancels. All right, guess what? Still doesn't exactly look the same. Well, almost, because pi minus 2x, so I mean it's a v, but it's the same thing because it's just a variable change, dummy variable, no worries. Then pi b minus b squared, so same thing over here. Okay, that matches up, but I have a 1 divided by sine v. That does not look the same. Well, applying some trigonometric properties / identities, we can actually write this as 1 divided by 2 times cosine of x squared times sine of x squared, which, reducing all that down, is going to give you the denominator is sine of x. So therefore, this whole thing is the same thing written as, let me actually just go back to the red for a second. This whole thing over here, I'm just going to circle this. This is the same thing written as 1 divided by sine of x. And so we can actually simply replace this. This is the exact same thing as that. So if I were to take the integral of this whole thing over here, that's the same thing over here. We're actually just back to simply just this inside function input over here. So by applying that, I have that ln of p of 1 is going to equal to just the natural log of x pi minus, well, I should really say v, since we are doing this in v. So I should really say v. So in this case, v times pi minus v squared, and then divided by tangent of v divided by 2. We evaluate this from, 0, and then pi divided by 2. And then we still have our subtract the 4 times g, and then divided by pi. Yeah, there's a lot going on, so that's pretty crazy right there. I told you this was going to happen. Okay, so now next thing to do is, of course, we have to, plug in our bounds. Simple enough. So if I plug in pi divided by 2 back into this thing, so I have the natural log. So let's see, pi divided by 2 times pi, so pi squared. And then the same thing over here, pi squared divided by 4, so it's pi squared divided by 2. Well, no, pi squared divided by 4 actually. So 2 and then a 4. So pi squared divided by 2 divided by 4. Plug in pi over 2 over here for the tangent argument. That's just going to be 1, so that's totally fine. And so now we're just left with the natural log of pi squared divided by 4. I can actually, go backwards and say we actually take out that exponent, so it's pi divided by 2 quantity square. Then utilize natural log properties, put that 2 outside, so I have 2 times the natural log of pi divided by 2. Okay, and then if I plug in 0, well, we have a 0, and tangent of 0 is 0, so we have a 0 over 0, so we actually have to, that's undeterminate, so we had to write this in terms of a limit. So v approaches 0 of the natural log of v pi minus v squared, and divided by tangent of v divided by 2. Okay, and then just 4 times g divided by pi. All right, so to save you the steps, I'm not going to write the entire steps and all, but I'll give you the full synopsis of everything and how to tackle this. So continuity of the natural logs, let's assume that the continuity of natural log exists specifically for at x equal to 2 pi, meaning I can now actually move this limit inside of our natural log argument. So it's the natural log of the limit of this entire thing. Well, you still plug v equals 0, you're still going to get a 0 over 0 indeterminate form. So to backtrack what I said earlier, it's not exactly indeterminate form, it's ln of 0, which is actually, it approaches, infinity? I'll have to put that in. But again, so natural log of this limit is going to be 0 over 0. You apply L'Hopital's rule, and so you get that the limit as v approaches 0. So take the the derivative. So I have pi minus 2 times v, and then on the bottom I have 1/2 times secant square of v divided by 2, which is fine. That if you actually just plug this all back in, you're going to get that this whole thing is just going to equal just the natural log of 2 pi. So thank we can thankfully say that this is completely not the hardest thing to, evaluate. So no more troubles there. And then, so this is what we have so far. So therefore, this is lead to the conclusion 2 ln pi divided by 2, subtract natural log of 2 pi minus 4 times Catalan's constant divided by pi. So this leads to say that ln, so just to reiterate, ln of p of 1 is equal to this entire thing. But now to combine some using natural log properties, 2 ln of pi divided by 2, so then subtract 2 pi, put that back together, you're gonna get that these two together is gonna combine, it's gonna equal to just the natural log of pi divided by 8 minus this. Last thing, let's just take e to both sides. P of 1, which is our given we want to calculate, is therefore going to equal to just pi divided by 8 multiplied by e to the power 4 times Catalan's constant g divided by pi. And so therefore this concludes our workload of solving this monstrosity of a but beautiful infinite product series, just like that. A lot of things going on. This part especially, I bet you were not expecting. I hit my door stopper, sorry about that. This is not what you were expecting for a step to actually come along the way that leads to such this monstrosity over here. So with all that being said, there you have it. And yeah, that's pretty cool if you ask me.